Welcome back to The Explainer. Have you ever just looked around at everyday stuff, your morning coffee, the smartphone in your hand, or even just the air you're breathing, and wondered how it's all actually put together? Well, at its core, chemistry is essentially the universe following a very strict, invisible recipe. So today, we're going to start from the tangible stuff we interact with every single day and zoom all the way down into the microscopic, completely invisible scale of atoms. We're going to uncover how this ultimate cosmic cookbook actually works.
Okay, let's dive into this. Our roadmap for the explainer today is pretty straightforward. 1. The basics of matter. 2. Laws of chemical combination. 3. Demystifying the mole concept. And finally, 4. Stoichiometry and chemical reactions.
But, before we even touch the heavy math of chemical equations, we've got to ask ourselves a really fundamental question. How do you count what you literally can't even see? Because before we can begin to measure the invisible mathematical rules of atoms, we first have to thoroughly understand how the physical matter right in front of us actually behaves.
All right, so Section 1, the basics of matter.
Just as a quick refresher, matter rarely just sits around completely pure on its own, right? It loves to mix. On one side, we've got homogeneous mixtures. Think of a 22-karat gold ring. It's got gold plus a little bit of copper or silver in there, but it looks perfectly uniform. You only see one single phase. Then, on the flip side, we have heterogeneous mixtures. Think of something like muddy seawater, where you can distinctly see the dirt, the salt, and the water separating out into totally visible components.
Moving right along to Section 2, Laws of Chemical Combination.
You can basically think of these 5 laws as the fundamental baking rules of the universe. We've got the conservation of mass, definite proportion, multiple proportion, Gay-Lussac's law for gas volumes, and Avogadro's law. Now, I know seeing a list of 5 scientific laws all at once might feel a little overwhelming, but stick with me here. We're going to break down the most crucial ones so they make absolute perfect sense.
Okay, so the very first rule is the law of conservation of mass, which classically says that mass can neither be created nor destroyed during a reaction. But here's a totally fascinating bit of trivia. Around 1905, Albert Einstein came along and added a tiny little addendum to this rule. He proved that mass and energy are actually interconvertible, beautifully captured by his incredibly famous equation, E=mc². So while we aren't destroying mass, it can absolutely interchange with energy. Wild, right?
Now, what's really interesting about this next slide is the law of definite proportions, which basically dictates absolute perfection. It states that if you want to make a specific chemical compound, you have to use the exact same ratio of ingredients by weight every single time. For instance, if the universe decides it wants to bake up some ammonia, NH3, it strictly requires a 14:3 ratio of nitrogen to hydrogen by mass. Not 14:4, not 15:3. It's exactly 14:3, no exceptions.
But wait, what if you use the exact same ingredients but in an entirely different ratio? Well, that is the law of multiple proportions. It's kind of like how combining flour and sugar differently can yield either a loaf of bread or a cake. Combining hydrogen and oxygen can make totally different things. A 1:8 ratio by mass gives you life-sustaining water, H2O. But a 1:16 ratio? That gives you hydrogen peroxide, H2O2, which you definitely, absolutely do not want to drink. The recipe changes, but it always locks into simple, whole numbers.
Which brings us nicely to Section 3, Demystifying the Mole Concept.
Behold Avogadro's number, 6.022 times 10 to the 23rd power. Guys, this is an astronomically, mind-bogglingly large number. To really put this into perspective, if you hold just 18 grams of water in the palm of your hand, which is honestly just a tiny little splash, that small puddle contains more individual water molecules than the roughly 10 billion people currently living on planet Earth. Atoms are just so unimaginably small, we literally need a massive number just to have a usable amount in a lab.
So the crucial point is this. Chemists needed a shortcut word for this giant number, and they called it the mole. Think about it. When you run to the grocery store, you don't ask for 12 eggs, right? You ask for a dozen. A dozen always means exactly 12. In chemistry, a mole simply means exactly 6.022 times 10 to the 23rd particles. It's really just a scientifically supersized dozen. That's the whole shebang. Okay, but how do we actually find out how many dozen or moles we have if we obviously can't count them one by one? Easy, we weigh them. The formula is wonderfully simple. The number of moles equals the given mass of the substance divided by its molar mass, which we can easily just pull right off the periodic table. And a quick tip here, while physics loves to measure things in large, bulky kilograms, chemistry is super delicate, so we always ensure our mass is measured in grams. Let's really ground this with a brilliant analogy using a compound like ethane, C2H6. Imagine you have a dozen AirPod cases. Since every single case naturally holds 2 individual earbuds, 1 dozen cases logically means you have 2 dozen earbuds. The exact same logic applies to molecules. If you calculate that you have 3 moles of ethane, it's exactly like having 3 dozen AirPod cases. Because the chemical formula is C2H6, you actually have 6 moles of carbon atoms safely tucked away inside.
All right, Section 4, the ultimate boss battle of chemistry. Stoichiometry and chemical reactions.
Stoichiometry is formally defined as the relationship between the relative quantities of substances taking part in a reaction. But I need to flash a massive warning sign right here. Stoichiometry relies entirely on counting moles or volume to balance equations. You absolutely cannot just balance the raw mass. Grams do not react directly with grams. Individual molecules react with individual molecules.
Let's move to and see how this builds into an incredibly reliable system. Whenever you face a chemical reaction, it's really just a strict 3-step process to get your answer. Step 1, balance the reaction equation. Step 2, convert whatever mass you're given into moles. Step 3, apply the stoichiometric ratio. Doing this greatly reduces your cognitive load, and honestly, it works every single time.
And this brilliantly illustrates the whole concept. Let's look at the actual recipe to bake some water. The balanced equation is 2H2 plus 1O2 yields 2H2O. This explicitly tells us we perfectly need 2 moles of hydrogen gas and exactly 1 mole of oxygen gas to yield 2 moles of water. Notice the math there? 2 moles plus 1 mole literally gave us 2 moles of product? Because again, we are counting packages here, not just adding raw heavy mass together.
But here's the catch. Chemists don't have a magical mole meter sitting on their lab benches. They just have a standard weighing scale. So once our stoichiometry tells us we need, say, exactly 5 moles of water, we have to translate that abstract concept back into the real physical world. We do this by simply reversing our formula. Mass equals moles multiplied by molar mass. For water, 5 moles multiplied by its molar mass of 18, because oxygen is 16 and 2 hydrogens make 2, means a chemist needs to weigh out exactly 90 grams on their scale.
Now, we don't always measure things perfectly in a real-world laboratory. And this brings up a genuinely fascinating question. What happens when the universe runs out of an ingredient mid-recipe? What if you dump in a ton of oxygen, but you completely run out of hydrogen halfway through? This introduces the absolutely crucial concept of limiting reagents, where the ingredient you literally have the least of completely dictates how much of the final product you can make, no matter how much extra stuff is floating around. But exactly how we calculate that messy lab scenario, well, that's a puzzle for next time. Keep analyzing those invisible recipes, and I'll catch you in the next explainer.